Dear students, today let us explore some important scenarios involving a straight conductor carrying a current and the magnetic field associated with it. This concept is very fundamental in electromagnetism, and it is also highly important for competitive exams like JEST, GATE and SET exams. In fact, many questions appeared in previously conducted exams like JEST and GATE, and based on the observations we may witness that in future too there may be a lot of chance to get some problems on this concept. So now let us begin. So if we take a straight conductor carrying a current of infinite length as shown in this figure. So here the straight conductor is carrying current in upward direction. So in this case what happens? Magnetic field appears around the straight conductor. So if the conductor carrying a current in upward direction, so what is the direction of the magnetic field? So according to right hand rule, this is the right hand rule. If we hold the straight conductor using our right hand, showing the thumb in the upward direction, that is current carrying direction, then the fingers of the curled fingers of the wire represent the magnetic field. So here if current is flowing in this upward direction, magnetic field is concentric circles starting from right side to and ending at the other side. So they appear from like this. That means they originate at this position and at this position. So if we represent magnetic lines originating from the sheet of the plane of the paper, so that's why we represent like this, and at the left side they go into the plane of the paper. At the right side they come out of the plane of the paper, and the right side they go into the plane of the paper. Okay, so this is the representation. We have to remember this. Okay, now what is the expression for magnetic field of a straight conductor? So it will be given by B is equal mu naught I by 2 pi r. So what is I? The current flowing through the wire. And what is mu here? What is mu naught? Mu naught value 4 pi into 10 power minus 7 per ampere, and r is the radial distance from the wire. That means, for example, this is a wire, and at a distance of r, I am asking what is the magnetic field. Then I utilize this formula. B is equal to mu naught I by 2 pi r. Then the direction we already discussed it. And if you observe here, what is the relation between B and distance? It is 1 by r. Here mu naught is a constant, 2 pi r is constant. So there is an inverse proportional between magnetic field and radial distance. If you draw the figure, it will appear like this. So taking radius distance on the x-axis and magnetic field on y-axis. So the graph will be look like this. Okay. So why? Because there is a inverse relation between magnetic field and the distance. That means this is a straight conductor. So there will be maximum magnetic field nearby the conductor. So maximum magnetic field will appear nearby the conductor, and there will be very minimum magnetic field at the far end. So similarly in this direction also. Okay. So entirely depends on the distance on the straight conductor. And so far I am telling this is for a straight conductor of infinite length. So then what about magnetic field due to a finite conductor? For example, if the length of the conductor is fixed L, then what will be the magnetic field at a point R from the wire? So for in this case, magnetic field will be given by B is equal mu naught I by 4 pi r into sine theta 1 plus sine theta 2. So what is the sine theta 1 and sine theta 2? So these are the angles subtended by the both ends of the wire at the given point. So here this is the theta 1 and this is theta 2. Okay. So that's it. Now let us see some scenarios based on this concept. So the first scenario is I take a straight conductor like this, carrying a current I, infinite conductor in a forward direction. Now, if there is a charge, say electron is flowing in this direction. That means, for example, if we consider the whole scenario in XYZ axis, okay, so our conductor is current carrying in Y direction. Okay, now the electron is moving in positive X direction, positive X axis direction. So then what happens in this situation? So what is the behavior? So will be there any force acting on the particle? So yes, just definitely the electron experiences a force. Then what is the direction of the force? As I said, if the straight conductor carrying current in the upward direction, magnetic field in the left hand direction will be like this. That means they go into the plane of the paper. Okay. Now the electron experiences magnetic field, perpendicular magnetic field due to the straight conductor. Okay. Then how to find the force direction? Okay. So here we have left hand rule. So here the particle velocity V is along x-axis direction I cap. Okay. And magnetic field direction is along negative x-axis direction. Why? Magnetic lines going into the plane of the paper. Okay. Then force acting on the particle is given by Q into V cross B. Right? Lorentz force. Okay. Now if I substitute Q into Q is the charge of the electron, Vi cap cross minus B K cap. Okay. So then if I simplify is final I will get Q V J cap. Why? Because I cap cross minus minus K cap will yield J cap plus J cap. Okay. So that means the particle will flow will go in the direction of positive Z axis, sorry, positive Y axis. So it will go positive Y axis direction. So that means the electron will travel like this. The force acting on this particle is in this direction. So here the original speed is along this direction. Original velocity is along positive x-axis, and due to the force due to straight conductor is along y-axis. So because of this, the particle will take a path like this. Okay. So this is important. We should understand the direction and the force acting on this direction, acting on the particle, and also final path of the particle. Okay. So these three are important. So now let us see another scenario. So now let us see another scenario. Here there is straight conductor, straight conductor carrying a current I. Now I am keeping a rod of finite length L. Okay, moving on positive x-axis direction. So in previous problem we have seen that a single electron, single particle, but here a straight conductor. Okay, so now what happens to it? As I said, the magnetic field due to straight conductor is B is equal mu naught I by 2 pi r. Okay, that means B is inversely proportional to r. That means magnetic field is not at all uniform. At the nearby the conductor, there will be a maximum magnetic field. At the far end, there will be magnetic field is very less. Okay, that means there is a varying magnetic field. That means the point, for example, this is A point and this is point. A point is nearby straight conductor. That means it will face maximum force compared to B point. Okay, that means there is a non-uniform magnetic field acts on the rod. So because of this, different particles experiences different forces. That means here it will be very maximum, it will be maximum. That means there is a force gradient or field gradient. Force gradient acts on the body. So because of this, the particle, the rod will experience a torque acting on it. Okay, so that means it will experience a maximum force and a minor force, a minor force, a minor force like this. So that means the rod will experience a force like this. Okay, so this is the scenario 2. Now let us see third scenario. That means here two infinite state conductors carrying current in same direction. See, for example, this is conductor A and this conductor B. Both are having same current I in same direction. Okay, so then what happens between them? Okay, so here I told the magnetic field direction for magnetic field A here. In this is the left side is magnetic field lines go into the plane of the paper, and due to magnetic field from the conductor B, they come out of the paper. Okay, so that means there will be attraction force. Okay, the two conductors attract each other. That means two straight conductors carrying current in same direction will attract each other. If one conductor having a current in upward direction, other conductor is magnetic field downward direction, then two conductors will repel each other. So this is very important point to be noted. Okay. Now based on this, we will do an important problem which is given in previous JEST exam. So the situation is, okay, now I take three straight conductors. Okay, so which are separated by equal distance. So here the distance between this wire and this wire is d, and similarly this is also at same distance d. Okay, now the twist is here, it is having a current in upward direction, and this is also in upward direction, and this is in downward direction. Let us say all are having equal current. Okay, downward direction. So then what happens? Just now I told, if the two straight conductors carry current in same direction, they will attract each other. If the conductor carry in opposite direction, they will repel each other, right? So now For example, I name it A, B, C. Okay. Now A and B. A will repel line B in this direction. Similarly, C will also repel B in this direction. That means it will repelled by A and B. The conductor B will be repelled by conductors A and C. Right. So because of this, it will suffer a vibration, oscillation. Okay. Now let us find the time period of the oscillation. So what is the time period of the conductor B? Why it is time period? Why it is having frequency or time period? Because it is being repelled by two conductors. It is exactly in midway between this both of them. Okay. So this question is very important. Now initially let us see that. So because of A, let us consider because of A, B is slightly displaced by a distance x. Okay. So let us say this is x. This is separated by distance small x. Okay. Now what is the difference? What is the distance between A and new B? So this will be d plus x. And then what will be the displacement? D minus x. Okay. So then what is the force between A and B? Force between A and B. So F is equal, I'm writing force per unit length. F will be mu naught I square by 2 pi r. Sorry, not is here. Distance is not r. 1 by d plus x. Okay. And similarly, force between B and C. Force per unit length. Okay. So it will also same magnitude. No, distance will be different. So d minus x. Okay. So then what is the net force acting on the B? Net force F net. Okay. So it will be mu naught I by 2 pi d minus x d plus x. So mu naught I by 2 pi cancel, get common, d minus x minus d plus x. Okay. So now if I simplify this, I'll get d plus x minus d minus of minus x plus x by d square minus x square LCM. So I get 2x by d square minus x square. So as d is very much higher than x, I can neglect x square term. So mu naught I by 2 pi I into 2x by d square. Here 2 get cancelled. So finally we will be left with mu naught I square x by pi d square. So this is the net force acting on the conductor B. Okay. Now I'm writing net force is mu naught I x by pi d square. So now let us compare this with F is equal minus kx, restoring force. If you remember spring forces, restoring force acting on the spring wheel, we taken F is equal to minus kx. So now we can compare with these two. Okay. So then we can write K is nothing but K is equal. Why here? Here we have X term, here we have X term. So then remaining term can be equivalent to K. Okay. So using that analogy, I can write K is equal mu naught I square L by pi d square. Okay. Actually, previously we mentioned we have calculated force by unit length. I take that L here. Okay. So then remember angular frequency, relation between K and angular frequency. Okay. How omega and K related. What is omega? Angular frequency. So omega is equal to K by M. Okay. Now I substitute that. So omega will be mu naught I square L by pi M d square. So what is M here? Mass. Okay. Mass of the conductor B. Okay. So then what is the time period? So what is the time period? So we know time period. If we know the frequency, we can easily find time period. So nothing but T is equal to 2 pi into pi m d square by mu naught I square L. Okay. So this is the time period. Why it is making time period? Why it is making oscillation? So because the middle wire experiences repellent forces due to A and B. So it continuously get repelled by both of them. So it will make some oscillation. So because of the experience, it processes a frequency and time period. Okay. Now